Hi everybody, we are continuing with our next presentation. Its title is Container Specialized Operating System at the Edge, Supercharge Kubernetes with Immutability. And our next speaker is Nicolas Vermande.
Yeah, that's the name.
I got the name right. Okay, so you can introduce yourself.
Yeah, sure, I'm gonna do it. I just want to check because the colors looks a little bit off, so yeah, no, it's good. I just wanted to check, like, in terms of contrast, if we can see everything. So it should be fine. So hi, everyone. I think some people may still be in a break because I understand that you had some, the previous session was going a bit over time. But that's fine. So the topic for today is going to be Container Specialized OS at the Edge, Supercharge Kubernetes with Immutability. So it's valid at the edge because edge has some specific requirements with security, operation, all that things. But also, I think it's still valid for data center or cloud or whatever is your Kubernetes use case. We're going to see the benefits of container specialized OS and immutability applied, generally speaking, in Kubernetes. So my name is Nick. I've been working with Kubernetes for the last 6 years on both CNI, CSI based companies. So I've been working at Cisco for about 7 years, been working at Storage OS, more on the CSI side of things. You can find me on social networks if you have any questions, burning questions, maybe next week or the week after, or if you want to know more about anything what we're doing. So I'm also the head of DevRel at Spectral Cloud. And so let's get started because we only have 35 minutes and I got to cover a lot of things. So the idea for today, I'm going to introduce what is Edge, what is immutability, try to get rather fast on that, to go into more of the different solutions. And we're going to see how to build Kubernetes clusters with those solutions, container specialized OS solutions. So why is Edge becoming a thing nowadays? So obviously with our current society, we are 100% connected, all day connected, and so are our industries. Whether it's connected device, industries, industrial, factories, retail, aeroplanes, everything runs some sort of operating system at the edge. Whether it's for real-time data processing, data caching optimization, manipulation analysis, and there's good reason to do that. Most of them are costs. It's a lot easier to process data at the edge where the information is. Once the data is processed, then you can send it back to your cloud or to your main data center. And that makes Kubernetes a very good candidate to run workloads at the edge. Modern application, you can package application as a Kubernetes application, or even better, you can package your application as a Kubernetes cluster, right? Completely wrapped as a Kubernetes cluster. Then to update your application, well, you just update the whole Kubernetes cluster, or just the deployment using Helm, this kind of things. But being that said, what you don't want to do is building snowflakes at the edge, right? So if you use a traditional operating system, obviously operation will involve things like patching the operating system, whether it's security, updating some packages, all that in a more imperative fashion, so that every edge location may look different from the others. And this you don't want to do, right? Because you need predictability, you need more security, and eventually at the edge you may not have the skill sets required to manage operation. Typically it's going to be operators that are not necessarily familiar with Kubernetes. So what are the key challenges at the edge? So deployment first, right? How do you deploy your Kubernetes cluster and the different application at the edge? And how do you provide day-to operations? Things like how do you upgrades? How do you update your application? All that should be some sort of atomic operations, right? If you leave the system live for too long, and then do changes, then you kind of drift away from the initial configuration or from your ideal declarative configuration. So we want to implement the same principle that we have in Kubernetes, declarative, in a declarative fashion. We also want to implement that at the operating system level. So of course, security at the edge is a challenge. Like if you're in McDonald's restaurant, someone can just steal the drives, or in a retail. So yeah, security is very important. Software footprint. So usually at the edge is a small system, so it can be as small as a Raspberry Pi or Intel NUC. So the software needs to have a small footprint. So the form factor, usually you can have a mix of virtual machine or bare metal server. So the version of Kubernetes you're using, the operating system, should satisfy all those form factors and ideally manage them in the same way. And as I was saying, skills may be limited at the edge location, meaning that if you need to upgrade something or update a system, it should be as easy as plugging in, like a USB key and just letting the system upgrade, or with a QR code, right? If you need to do more than that, if you need more skills to upgrade, then it may be very cost inefficient for the company implementing those edge locations. Okay, so, but ideally, immutability will respond to those requirements, but what is immutability? So who is familiar with this concept, immutability? Some of you. Okay, cool. But just in a nutshell, I wanted to just give you a couple of definitions and what are the different characteristics for an immutable system. So we have, first of all, a static file system, meaning that some of the partitions are read-only, except for user data. So typically where you will have some state that is maintained. It can be things like, logs, or can be, of course, your own, external storage to store databases or things like that, or running databases in Kubernetes. Your PVC should be able to persist over time, right? Another thing that is very important is atomic updates. It just means that you should consider your Kubernetes cluster as your iOS or Google phone. When you upgrade, it should be replacing the entire system. So even if you have one package that is different, you don't want to just replace that package. You just want a new image to be deployed into your system, right? This is something that is very important. And then in case of failure, you can also have, you want an easier rollback. If the system doesn't boot anymore, your OS should be intelligent enough to roll back to the prior version. So of course, predictability is a direct consequence of immutability, because you don't allow for any drift from the initial configuration, from the desired state. You don't have any configuration drift. And finally, also security. So typically, you want a static init.rmfs or init.rd that is compiled with the operating system, even if you have like someone that is or a malicious persona that wants to tamper the init.rmfs and reboot the device so that it behaves in another way as initially, then it won't be able to do that, because obviously as the system reboots, then it reverts back to the initial configuration, including for the init.rmfs or init.rd, which reduces the attack surface. Okay, so this is all the characteristics that we are going to see in the systems, in the different solutions that I'm going to show you in a minute. But first, how would you choose the best container-specific OS? So we've seen that container-specific OS have immutability at their core. That's one of the a given. That's a given. This is one of the characteristics you cannot make any trade-off about. Ideally, you want some automated, orchestrated deployment of those operating systems. You don't want to be going, one by one on every node in the cluster and deploy that operating system. It should be easy to deploy, orchestrated. Should support things for increased security like disk encryption. OS customization is also nice to have. Ideally, if you are, a Ubuntu shop, maybe you want to continue to use Ubuntu and make it immutable. We're going to see, what kind of solution may allow you to do that. And we'll see that some other solutions are, very opinionated. So you may have to, to implement some trade-off there. You want a declarative configuration model, ideally. So typically, all those systems will provide some sort of extensibility using Cloud Init. And also, something that is really nice to have, in the same way that, I don't know if you guys are familiar with Cluster API, some of you? Yeah, no, maybe one or two. So the idea of Cluster API is to build Kubernetes from Kubernetes by using custom resource definition and extending the Kubernetes API. So what that means is that you can create your own objects in Kubernetes and make them first-class citizen. And that includes the operating system running Kubernetes. So what that means is you can create, what you want ideally is to be able to manage not only Kubernetes, but the underlying operating system using Kubernetes native objects within Kubernetes. So for example, if you want to create a new OS artifact, it should be a custom resource instead of a pod. You can call it like OS artifact, and then you can have this operating system as an artifact running in Kubernetes. So it can be an ISO, can be another type of image, but it is already running in Kubernetes. So now the only thing you have to do is do an API request, like a curl from a Kubernetes service, and download the ISO from that particular service, so that you can have the whole lifecycle of Kubernetes using Cluster API, and the operating system using also CRDs as Cluster API, everything within Kubernetes. So now you're not only using Kubernetes as the platform to run your application, but also as the platform to deploy Kubernetes, right? So it's like eating your own dog food. So now you only have to learn one thing, which is Kubernetes in the end. And then finally, what you also want, again, this is probably nice to have, is your container specialized OS solution. It's much more than an OS, right? So ideally, you want to have this strong relationship, this strong link between the OS and Kubernetes. So ideally, have some sort of Kubernetes installer as part of the solution providing this container specialized OS, right? So it's a whole operating system and Kubernetes, two different layers, but with a strong bond between themselves, right? Okay, so what are the current solutions on the market? So today, they are everything is open source here. This is the one we're gonna see today. Most of them. We're gonna see, so K3S typically is the Kubernetes distribution you run at the edge, because it's just a simple set of binary with like a light database if you want, or it can also be etcd. But yeah, it does have a small footprint, so more ideally, like for the edge, although you can also run it for your main Kubernetes solution in the data center. We're gonna see Bottlerocket here from Amazon. Thalos Linux, which is also part of the CNCF ecosystem. Flatcar. We're not going to talk about K3OS because the project is pretty much non-developed anymore. And Kairos. So Kairos, I'll keep it for the last portion. So it's an open source project, not that old, but probably it's like 2 or 3 years. It's sponsored by Spectral Cloud, my company, but it's fully open source. We had contribution from Intel, Facebook, so I keep it for the end. But here I'm going to give you an unbiased version of all those solutions. And for this, I'm going to go solution by solution on how, the experience you would go through if you were deploying Kubernetes yourself. I'm not going to do it live because I have 20 minutes. But I'm going to give you the high-level procedures, then the detailed procedures through command and scriptshoot. And I'm going to insist on the main, the main phases, the advantages and drawbacks, and some of the caveats I've noticed. At the end, there will be a QR code. I've published a blog post probably a couple of months ago, 30 pages, even more details on all those solutions. So if you still want to learn even more, so you can follow that particular link in the end. So let's start with Flatcar. So Flatcar Container Linux. It's been forked from CoreOS. So CoreOS, has been developed a long time. So who's familiar with CoreOS or heard about it? Me, a couple of you. So that was one of the first container specialized OS. So people like Kinvolk, which basically is the remaining people from who have been building CoreOS Linux, they have forked it into a Flatcar. So it can be used as just as an operating system or as an OS plus Kubernetes. And we're going to see how we can deploy K3S essentially on top of Flatcar and build a cluster. So at the very foundation, the Flatcar container Linux is an OS that is bootstrapped via a curated image, which means that you download an image from somewhere. So it is by nature opinionated. Then you can provide extra configuration via Cloud Init. So hopefully everyone is familiar with Cloud Init, which is just a YAML customization of your cloud image so that you can customize and install things and configure things in your OS. So here, you can combine Cloud Init and systemd unit file to install Kubernetes, which is kind of do-it-yourself. There's not a strong bond between the OS and Kubernetes, right? It's really kind of do-it-yourself. We have multiple components, so essentially two. We have Ignition, which is like the machine format JSON schema that powers the customization of the container OS, right? And then we have Butane. So Butane is the corresponding user-friendly YAML configuration. So what that means is that you configure a YAML file specifying all your extra configuration via Butane. You transpile it into Ignition JSON, and then you inject this into your image, and then you have a custom operating system. A couple of things that are interesting: you have automatic system updates. You don't have to do anything, and the system will reboot with a new version. So A/B sort of partitioning. You can download ISO for your bare metal use cases, which is very good at the edge. And it does support, as a sort of beta feature, I would say, Cluster API. So again, Cluster API, deploying Kubernetes from Kubernetes. With the image builder portion of Cluster API, which is, Cluster API needs a based operating system. This can be Flatcar. And the Ignition bootstrap configuration for the customization is also available within Cluster API, but this is really alpha. So slowly Flatcar is being integrated with Cluster API, and at this stage we have a very strong bond between Kubernetes and the OS because we have Cluster API managing the Kubernetes lifecycle as well as the operating system. So here, for all the solution, we're going to deploy a K3S or a Kubernetes cluster, depending on if it supports K3S or not, in various environments. So here, this is going to be in Google Cloud Platform. So at high level, this is the steps. So first, create the Butane YAML file for the control plane. Then create the Butane YAML file for the worker node. As I was saying, transpile or transpose, or transpile is the term they are using, from Butane to Ignition, so that you have the JSON document. And then for every node, you deploy the Flatcar cloud image with the Ignition configuration ingested as cloud metadata, right? We're going to see how to do that, and then verify that it is going to deploy Kubernetes, create the cluster. And then you have a strong, differentiation between workers and master. And we're going to see it's like something that will repeat over the different solution. Either you have to create worker and control plane, configuration in a different way, or sometimes, depending on the solution, you can have like a self-elected process that will elect some master and workers. But here is distinct. So the first thing here is an example of the Butane configuration. So as I was saying, it's quite do-it-yourself, where you install K3S via the traditional K3S systemd unit file. So you have to know how to do that. You have to go through the documentation. It's classic systemd unit files. Nothing new here. The only thing you need is the K3S installer, and this is exactly a cloud init configuration file, right? So there's nothing really new here. So you do the same thing for the workers, and you can see that you have to specify the token in clear text. This is just as an example here. And you have to specify also the control plane node IP in the worker configuration, which means that it has to be sequential. First, you deploy the control plane nodes, and then you deploy the worker nodes. So slightly difference here, you know, like just the command line will be different, whether it's the worker or the control plane. And then you create the ignition configuration using a tool so that it's transposed into JSON. So here I'm using a Docker container. So I'm piping the YAML file into a Docker container for the control plane JSON file, and the same thing for the node, the worker JSON file, right? So now so ignition underscore CP and node.json are my ignition metadata I need to inject into my cloud image. And then because it's Google, they make it very easy. So to inject, so Flatcar has essentially, as you can see on the image family, on the image project, you can find the GCP image already there. The only thing you have to define is the zone, the machine type, and then inject your ignition file as part of the gcloud command line. So here is the control plane. And as you can see, as mentioned before, you have to create the control plane first. After a couple of minutes, you know, if you keep the default settings, it's quite fast. You've got a control plane nodes there, right? And then same thing for the worker nodes. So you can see here, I'm creating two instances, Flatcar 2 and Flatcar 3. Same thing again, image project, image family, and then I'm just specifying the ignition node, the JSON that contains the information for the worker nodes. After a couple of minutes, you can see again, Flatcar 2, Flatcar 3 are popping up. And then you can, the last part is checking that the cluster is healthy. So here I'm just creating an SSH session into my control plane node, which is Flatcar 1. I'm just doing kubectl get nodes, and as you can see here, I end up with control plane, role etcd, master, have the right Kubernetes version I want through K3S installation, and that's basically it, right? So it's quite fast, but at the same time, it's quite opinionated. Like to update the K3S version, well, it is going to be a bit more complicated because I have to change the K3S version via the system unit D file. And for the update of Flatcar itself, I can rely on the automatic updates, right? So the automatic updates is just going to update the operating system, not the Kubernetes or the K3S application in that solution. So we are kind of disjoint between the OS and Kubernetes, except again if you use the cluster API method I've mentioned before, but as I said, with caution because it's still quite new. Okay, now the second solution. So that was it for Flatcar. Let's examine Bottlerocket. So Bottlerocket has been created in 2020 by Amazon. And it's written in Rust, so I don't know if if we have some Rust fan in the room, but yeah, it's quite an interesting project, and ultimately it's meant to be used, I mean, not only, but let's say the primary use case is within AWS. So if you're an Amazon or AWS customer, that may be the right solution for you. And it is integrated with a plethora of AWS services such as EKS, ECS, Fargate. I mean, you have all the list here. Some specificities, so it's using TUF, it stands for the update framework, which is also a CNCF graduated project. And actually, it's a set of protocols and tools that aims to secure software update systems. So, and this is what Bottlerocket is using to secure updates and secure the whole system. It can be a pain in the neck, we're going to see. But yeah, it's more secure. But there's always a trade-off, as you probably know, guys, between security and flexibility, right? So specificity, it's solely configurable via API with secure out-of-band access methods, no SSH server or even a shell, and there's no variant for K3s. So it's very opinionated. You cannot customize a lot of things. And you have to pick up the base image for both the OS and the Kubernetes version. And we're going to see there are some challenges with this. And last but not least, it only works for worker nodes. You have to have a control plane, which kind of, in my opinion, sort of destroyed the purpose, but this is how it is. It's only for worker nodes. So at a high level, we're going to see like in VMware how to do it, because yeah, it's probably for the edge. It's also a good use case where you have virtualization running locally. You update the OVA in vCenter, create Bottlerocket VM from the template. You create a Bottlerocket configuration file, inject the Bottlerocket user data via the guest info interface, which is the same as user data in the cloud. VMware has the same thing. It's called the guest info interface. And then you verify that the VM have joined the Kubernetes cluster as worker nodes, right? This is essentially kind of the same steps as before. So the first thing we have to go is install GoVC. This is the way I like to do things in VMware, because GoVC is just a CLI that allows you to do any operation in VMware with a command line instead of clicking and using the UI. So it's very useful if you want to automate. So we have to use Rust. So we have to install Rust. We have to install Cargo, which is the Rust package manager, and also allow you to build your Rust project. And the TUF tool, which is the CLI command that correspond to TUF. So that's a lot of prerequisites. So the first thing we have to do is download and check the Bottlerocket root role from TUF. To verify the OVA, and then download the OVA variant locally, right? So you can do that using curl. This is where you download the JSON role for the root. And then you use TUF tool to download the OVA using all those variables. But basically, you specify the metadata, you specify the OVA you want, the variant, the version, all of that. So it's very opinionated. Like you can't do much customization at this level. You have basically to copy paste that to get the OVA. And then generate the OVA specification. Once you have the OVA, you have to extract the specification file from the OVA, customize that, adding the network information, and then re-upload this configuration into vSphere together with the OVA and create the worker VM. So for this, you use GoVC. You import the OVA into a JSON specification. You edit that specification to add the network name here, to add the network name. Here, GoVC network. You want to add this into your specification so the VM are deployed in that network. And then you re-import the OVA with that specification file into vCenter. And then you use GoVC to deploy 3 workers, like simply in a loop. I'm just cloning that particular OVA into 3 different VMs. And then you have now how those VMs will differ, right, in terms of configuration. This is where you have to create the Bottlerocket user data and inject it into those VMs. Same principle as before, except that in VMware, instead of using the metadata from the cloud, we are using a specific interface, which is the guest info interface, and the user data that is there. So the user data is essentially, again, copy-paste from Bottlerocket configuration, where you specify the API server, the cluster DNS IP, the bootstrap token, and the cluster certificates, all of that, and you have the command on the top on how to do that. But again, not much to derive from that. You have to do it this way, and that's about it. And then you just encode this in base 64, and that's basically it. It's injected into your VM using that command. And then you check that the Kubernetes cluster is healthy. Just here we are doing kubectl get nodes, and you can see the different pods as provision. And that's essentially it. So again, same thing, but very, very much opinionated. So Thalos, so yeah, still 5 minutes. I may take questions after. If you want, yeah, I'm not sure we're going to have time for questions, but if you have some questions, I will be outside anyway. So Thalos has been released in 2018 by Sidero Labs, even more opinionated than Bottlerocket. doesn't have any SSH. You manage everything via Thalos CTL, like kubectl. And this is probably the solution that is that provide the most integration between Kubernetes and the operating system. You manage everything as a whole, in a declarative fashion via YAML, right? So same way of completely Kubernetes native. It does have a cluster API provider for both Bootstrap and the control plane, and it provides very easy upgrade, this time both the OS and Kubernetes, using a single command line. Like here, for example, Thalos CTL, upgrade Kates, --2, and the version, right? As easy as that. You can also create your own Thalos cluster locally, like you would do with Minikube, by using Thalos CTL cluster create. It has a variety of support for, like machine learning, NVIDIA GPU, NVIDIA Fabric Manager, support disk encryption. It supports highly available control plane natively without load balancer, which is great. You don't have to go through this, extra steps to make your control plane highly available. It's just using a VIP, like a floating IP. But again, very opinionated. Customization is limited to the kernel modules and to the file system content, which reduces the hardware it does support. So not necessarily the right system for edge use cases. Also have a public key infrastructure, of your Kubernetes cluster baked in. And it does support WireGuard peer discovery if you were to run a Kubernetes cluster over the internet. So here again, this time highly available cluster because it's super easy. High-level step, generate the base machine configuration for the control plane and the worker nodes via the Thalos CTL command line. Upload OVA, again, you have to find the right OVA to your vCenter. Deploy and start the control plane nodes, bootstrap the cluster, and start the worker node. So it's like a two-step process. So the first thing to create your Thalos configuration, you just download a template from this page here, this repository, if you wish. And then only for the control plane, if you want to go simple, you just specify the VIP, and that's the only thing you have to modify. Right. Once you have this file, you just use Thalos CTL gen config with the IP address here, which is your VIP, and specify the patch file, so the file modified, and then it's going to create the control plane configuration, the worker configuration, and your Thalos configuration. So pretty opinionated, but super, super fast. Because now, the only thing that you have to do, again, is download and install the OVA, same way as before. I didn't specify how to do it there, with GoVC, and specify the user data, again, via the guest info interface. So the path is a bit different here, .thalos.config, but essentially the same thing. You just encode the configuration via base64. Deploy the VM here for the control plane. So we have 3 control plane nodes. And repeat the same operation for the worker nodes. Same thing, except that Thalos has generated both the worker and master configuration. So here, instead of the control plane, it's the worker configuration. And here I'm adding 2 worker, right? Simply specifying some hardware configuration. And that's it, super fast. It does basically all the job for you. Bootstrap the cluster using Thalos CTL again, the bootstrap command, retrieve the kubeconfig file, and check that okay, thank you. And then check that the cluster is healthy, right? The only thing is a bit better, I think, about Thalos. It's also installing the VMware tools, which may be very handy if you want to extract information from vCenter. It runs that as a daemon set, which is quite smart, I think. Okay, the last one, in 1 minute, Kairos. So Kairos, as opposed to the other solution, is I think, the one that is the most flexible because it's an OS factory. We can turn any OS into an immutable system using container images. So we build full-fledged OS from container registry. Can be any container registry. It can be like Ubuntu, it can be your own. We also provide like OS images as the other solution, but you can fully customize the OS from the kernel, from the packages, anything you want, and turn it into an immutable operating system, and you can define what you want to be persistent, one node out of time. Okay, thank you. I'm going to try to make it super fast. But basically, you can construct the OS based on container images and also use it in a cloud init configuration. So cloud init is going to be used to configure the customization as well as the Kairos features. We're going to see just a couple of Kairos features, and you can bootstrap Kubernetes from Pixie, just as a DHCP proxy, which means that you don't have to boot anything from an image or anything. It can be just via the network. So it does have a lot of configuration and options. We support highly available Kubernetes deployment with kubevip and P2P protocol with a distributed ledger like Bitcoin, if you like, to elect like the master and who will be the master nodes, who will be the control, the worker nodes. You just define how many control planes you want, right? We support OS artifact as custom resources, as I was mentioning before, like Cluster API. We just deploy, you can generate artifacts, so ISO images, using Kubernetes and download from a Kubernetes service your ISO. And then you can boot that ISO from the network using Aurora Boot. Upgrades is done via the system upgrade controller from Rancher, or you can do it manually on every node as well. But I would recommend using just upgrading the cluster from Kubernetes itself using a YAML file. Again, a lot of security, disk encryption via TPM. We have partnered with Intel for the secure edge native architecture, which is a way to deploy securely at the edge. And we also support VPN overlay that can be very efficient if you're using DHCP for Kubernetes, because it allows you to have a stable IP on top of the DHCP IP that will never change.
I'm really sorry to cut you off, but we are...
Yeah, that's fine. I'm just going to conclude. 30 seconds. So here I'm just showing like a Docker file, as easy, can be any image, as mentioned. We can create, here you have an example of the Kairos configuration. Again, it's a simple file. And then you run the Aurora Boot container, boot it from the network, and the end result is that you end up with the right number of nodes, master or worker. Is going to be defined, you just specify the number of worker nodes that you want, as easy as that. So just to finalize the key takeaways for today's, security is key in Kubernetes. It starts with the underlying OS. So container specialized OS is the way to go, as recommended by NIST. But to choose your OS for Kubernetes can be hard, and you must define your priorities and pick the one that suits you. If you want to spend more time on that, you will have much more details. You can scan this. There's a full blog about that. I mean, it's a blog. It's more like a white paper. And for Kairos, if you want to learn more, you can join the Slack channel. We have office hours. And thank you.
Thank you very much. The question will be answered in person. So Vieroš, please find the speaker and you can get your answer.